Welcome to our Engineers Newsletter Live program. Today we'll be discussing fans and air handling systems. I'm Jeannie Harshaw from Trane's System Engineering Department, and I'll be your host today. Before we dive into today's program, let's take care of some housekeeping. This program is registered with AIA-CES and USGBC for continuing professional education. If you are an AIA member, this presentation qualifies for Sustainable Design Credit, so make sure you provide your member number to your local host before leaving today's session. In several states, certificates of completion can also be applied to engineers' continuing education requirements. So please check your state's rules to see if this might apply to you. We have a lot of information to cover today, so please fax in your questions during the program to the number on the screen or email us at enl@trane.com. We'll respond directly to you, so please remember to include your email address. Answers to all questions will also be available in a few weeks, so be sure to follow up with your Trane sales office for a copy. Now, many of you might be asking, why a program on fans? Well, as members of the Trane Applications Engineering Group, we hear firsthand from customers about many of the common problems with fans. Now, most of these problems, including low airflow and noisy operation, could easily be avoided with a little more knowledge about fan selection, a little more scrutiny of duct design and fan installation, or a little more thought about actual system operation. Our goal today is to give you, the designer, a solid understanding of fan basics, an overview of various fan types and their characteristics, an understanding of fan selection limitations, and how all of these elements come together to deliver a quiet, effective air delivery system. And finally, we'll discuss ASHRAE 90.1 requirements. To cover this information today, we have Dennis Stanke, who will provide a crash course on fan fundamentals. Dave Guckelberger will cover fans from the perspective of acoustics. John Murphy, an applications engineer, and Dustin Meredith from our Lexington Applications Group will walk us through fan and unit selection considerations. Dennis, would you get us started with some fan basics?
Sure. Today we're going to talk about fans, and I don't mean Houdat fans. I mean mechanical fans, the heart of every air distribution system. Fan fundamentals begin with air pressure. Air in motion has both potential and dynamic energy. Potential energy relates to static pressure, like air in a balloon. Dynamic energy relates to velocity pressure, like air pushing on a sail. The total pressure of air in motion is its static pressure plus its velocity pressure. A fan increases the total pressure of air passing through it. We represent fan operation using a fan performance curve. Basically, it's an XY plot showing the pressure that a fan can produce at different airflows while operating at a constant speed. The x-axis shows volumetric airflow rate in CFM, and the y-axis shows pressure in inches of water column. Most published fan curves show static pressure rise across the fan on the y-axis. It would be just as easy to show total pressure rise. In fact, AMCA might require it in the future, but for now we'll stick with the traditional approach and just show static pressure. Manufacturers determine the shape of specific fan performance curves using laboratory tests defined by industry standards. AMCA Standard 210 explains how to test fans in the lab, how to rate fan performance, and how to construct fan curves from the test data. Many manufacturers use the test configuration shown here. It can produce highly accurate airflow measurements over a wide range of flows, as well as very accurate pressure and power measurements. Tests run using this setup usually provide the most accurate fan performance data available. Air handler manufacturers also comply with AHRI 430 to rate unit performance. This certification standard requires unit-mounted fans to be tested in their cabinets so that cataloged fan performance includes these internal losses. For draw-through configurations, it's common to mount a coil upstream of the fan to account for loss in fan performance due to inlet turbulence. And for blow-through configuration, it's common to mount a blank section and a coil downstream of the fan to account for any losses in fan performance due to turbulence at the outlet. This way, system designers don't need to compensate for internal system effect losses when selecting air handler fans. Of course, designers do need to compensate for external system effect due to duct connections to the unit. We'll talk more about that in a few minutes. Fan performance testing is done at a given fan speed. For each test point, fan airflow is set by the test chamber exhaust. Accurate measurements of airflow, pressures, temperature, and so on are recorded along with the power required at the fan shaft. These data points are then used to construct a fan curve and brake horsepower curve for this specific fan in this test chamber at one speed and one air density. But a fan performance curve at one speed isn't very useful. We need a family of curves to show performance at several different speeds. To create this family of curves, tests could be run at many different fan speeds, but that really isn't necessary. We can use the fan laws. The fan laws are equations used to represent the relationship between parameters for similar fans at similar flow conditions used in the same system. Depending upon where you look, these equations are represented using different variable symbols and different numbering schemes. But regardless of the form of the equations or how they're numbered, they can all be derived from those found in Appendix D of AMCA 210. If we know the fan airflow rate for a certain type of fan operating at a given speed in a given system, for instance, we can use equation D2 to find a new airflow rate at a different speed or with a different fan diameter. If we know the total pressure at one speed, we can use equation D3 to find a new pressure at a different speed or a different fan diameter or a different air density. Similarly, we can find brake horsepower, velocity pressure, fan static pressure, and fan static efficiency. But we cannot use the fan laws to find the performance of one type of fan based on the performance of a different type of fan. And we cannot use them to find how a fan in one duct system operates in a different duct system. So we use fan data collected at one speed along with the fan laws to create fan performance curves for different speeds. If we use lab data to construct the 1200 RPM fan curve, for instance, we can use the fan laws to construct the 1000 RPM fan curve. Let's look at one point as an example. At 1200 RPM, this fan delivers 7500 CFM at 3.9 inches static pressure. Using equation D2, we find that it delivers 6250 CFM at 1000 RPM. And using equations D3, D5, and D6, we find that the fan requires 2.7 inches static pressure. These new values for airflow and pressure define one point on the 1000 RPM curve. Repeating these calculations for each test point results in a complete fan curve at a new speed. Similarly, new curves for brake horsepower can be developed. Here's an example of the actual fan curves for a specific fan in an air handling unit showing how the fan works at different speeds. The brake horsepower curves show how much power the fan needs at each operating point. Fan static efficiency lines could also be included. They're usually not published, but fan static efficiency can always be calculated at any operating point using the equation shown. In any case, we can use this family of fan performance curves to help select the right fan and fan speed for a required airflow and static pressure in a given system. But first we need to know how the system itself works. In other words, we need a way to describe the flow versus pressure characteristics of the air distribution system. Here's a pressure gradient plot for a VAV system. It shows both total pressure and static pressure. AMCA defines fan static pressure as the difference between outlet static pressure and inlet total pressure. So the total static pressure rise across the fan is the sum of the fan static pressure and the inlet velocity pressure at a given flow. The total change in static pressure through the air distribution system equals the total static pressure across the fan. This is what we plot on the y-axis of the fan curve. The total static pressure needed to move air through any duct system varies approximately as the square of the airflow. We represent the pressure flow relationship as a system resistance curve on the fan curve plot. Now there's one more important item that shows up on any fan curve. It's the do not select area defined by the surge line or stall line. Knowing this area is important. The rotating fan wheel produces a pressure difference from the inlet to the outlet. The whirling blades keep the air moving against this pressure as long as enough air enters the fan inlet. If the fan doesn't get enough air at a given speed, the air temporarily reverses direction and surges backward through the fan. This reverse flow can cause a noticeable fluctuation in both airflow and fan static pressure. All fans surge at some airflow, so to avoid it, a minimum airflow limit is established at every speed for every fan. This limit defines the do not select area to help designers select fans that won't surge. The surge limit depends on the fan type, and it can vary widely. For example, it may be 25% of wide open airflow for forward curve fans, but for vane axial fans, it may be 60% of wide open. Okay, now we know some basics about fan curves, fan laws, and system curves. They're developed using AMCA 210 and AHRI 430 test procedures and the fan laws, and they tell us how a fan works. System resistance curves tell us how a duct system works. Together, the fan curves and system curves help us predict how a given air distribution system will work. These basics apply to all systems with all types of fans. Now Dustin and John will tell us a little bit about different fan types.
Air handling units are typically available with several choices of fan types and sizes. This affords the opportunity to select a fan to best balance energy efficiency, acoustics, and cost. The most common type of fan used in an air handling unit is a centrifugal fan, in which air enters the center of the fan wheel and follows a radial path through it. A centrifugal fan may be characterized in a number of ways. The shape of the fan blades and whether the fan includes a scrolled housing are traditional ways to characterize. Other ways include whether the fan is belt or direct driven and whether single or multiple fans are used. Let's start with the shape of the fan blades. A forward curved or FC fan has blades that are curved in the direction of wheel rotation. These fans are operated at relatively low speeds and are used to deliver large volumes of air at relatively low static pressures. Due to the inherently light construction of the fan wheel, FC fans usually cost less than fans with other blade types and are typically used in smaller systems that require static pressures of about 4 inches or less. But FC fans are usually less efficient than other fan types.
The typical application range of an FC fan is between about 30 and 80% of wide open CFM. Now this doesn't mean they cannot operate outside this range, it's just the typical range. Operating below about 30% may result in unstable operation, and operating beyond 80% will typically be noisy and inefficient. The maximum static efficiency of an FC fan is between about 50 and 65%, and this occurs just to the right of the hump on the fan curve.
Because of this wide application range, and because FC fans have a less severe surge characteristic than other fan types, they are often the most forgiving choice. This makes them very popular in packaged and light commercial equipment. A backward curved or BC fan has shaped blades that are curved away from the direction of wheel rotation. A backward inclined or BI fan has flat blades that are slanted away from the direction of wheel rotation. The more rugged construction of a BC or BI fan allows them to operate at higher speeds than that of FC fans, making them suitable for higher pressure applications.
The typical application range of a BI fan is between about 40 and 85% wide open CFM. Their maximum static efficiency is between about 65 and 75%, and this occurs around 50 to 60% wide open CFM. So BC and BI fans are typically more efficient than FC fans.
Since the magnitude of surge is related to pressure, the surge characteristic exhibited by a fan of this type is usually more severe than that of an FC fan, considering BI and BC fans are typically used in higher pressure applications. A refinement of the BI fan changes the shape of the blade from a flat plate to an airfoil similar to an airplane wing. This smooth airflow across the blade surface reduces turbulence and noise within the wheel. The result is that an airfoil or AF fan is typically more efficient than the other fan types.
The typical application range of an airfoil fan is between about 50 and 85% of wide open CFM. Now this is narrower than either an FC or a BI fan because an airfoil fan typically enters surge at higher airflows. And at these higher airflows, the surge is often more severe than other fan types. But static efficiencies can be as high as 80 to 85%, usually making them the most efficient choice. As an example, let's consider a typical VAV air handling unit that has a draw-through supply fan that discharges into a straight section of duct. Operating at 13,000 CFM and a total static pressure of 3.8 inches, the forward curve fan needs to rotate at about 775 RPM, and its brake horsepower is about 13. The more efficient airfoil fan operates at a higher speed, 1320 RPM, but requires less horsepower at 11.8.
To summarize this section, forward curve fans are typically the lowest cost centrifugal fans. Because they have a wide application range and exhibit less severe surge characteristics, they are also often the most forgiving choice. This makes them very popular in packaged units and light commercial equipment where there is a tendency for less attention to be given to duct connections and layout. Airfoil fans are typically the most efficient, but because of their narrower application range and their tendency to have more severe surge characteristics, they do require more attention to avoid problems. This makes them more common in larger packaged rooftops and applied air handling units, where more attention is usually given to proper duct connections and layout. Airfoil fans usually run at higher speeds than FC fans, so they can be louder. But because they result in less turbulence, airfoil fans are usually quieter in the low frequency octave bands, which are the most difficult ones to attenuate. Another way to characterize a centrifugal fan is by whether it's a house fan or a plenum fan. A house fan contains a scroll or housing that directs the air leaving the fan in one direction. A plenum fan consists of a centrifugal fan wheel, typically with airfoil blades, without the surrounding housing. The fan wheel pressurizes the surrounding plenum, allowing air to discharge in multiple directions. Historically, most large fans used in HVAC systems have used a drive kit consisting of one or more belts and associated sheaves to connect the motor to the fan shaft. However, as variable speed drives have become more cost-effective and reliable, direct drive fans have become more popular, primarily with plenum fans. With a direct drive plenum fan, the fan wheel is mounted directly on the motor shaft. With no belts or sheaves and fewer bearings, direct drive fans are more reliable and require less maintenance than belt drive fans. And since there are no belt-related drive losses, direct drive plenum fans are typically more efficient, quieter, and experience less vibration than belt drive plenum fans. Because the motor is in line with the direction of airflow through the air handling unit, the motor mounted behind the fan wheel does not restrict airflow, does not stick out the side of the unit, and it does not increase unit width. However, the air handling unit may need to be slightly longer to accommodate the motor mounted behind the fan wheel. Depending on the location of the fan within the air handling unit, a plenum fan may be more or less efficient than a house fan. Let's take a look at a few example selections. A house fan is specifically designed to discharge into a long, straight section of duct that is about the same size as the fan outlet. This minimizes energy loss as velocity pressure is converted to static pressure and turbulence dissipates into laminar flow. With this discharge configuration, a housed airfoil fan will typically require less power than a plenum fan, but a plenum fan will likely have lower discharge sound levels.
Using our same example VAV air handling unit, with this discharge configuration, the housed airfoil fan requires 11.8 brake horsepower compared to 14 for the belt drive plenum fan and 12.8 for the direct drive plenum fan. While the housed fan requires less power, the plenum fans will typically have significantly lower discharge sound levels. The reduced sound levels occur partly because air velocity dissipates more quickly as the air pressurizes the plenum surrounding the fan, and because the plenum provides an opportunity for some of the sound to be absorbed before air discharges from the unit. The direct drive plenum fan reduces sound levels even further because it does not have the belt-related drive losses and associated noise, and because there are no obstruction in the inlet and the motor is mounted behind the fan wheel, it does not restrict airflow leaving the fan. Of course, this chart compares discharge sound. On the inlet side, plenum fans will usually have higher sound levels than house fans. So depending on the fan's location within the air handling system, either discharge or inlet sound may be more important. So the best fan choice depends on the application.
So, if the air handling unit has a draw-through fan that discharges directly into a sufficiently long, straight section of duct that's about the same size as the fan outlet, a housed airfoil fan will typically require less power than a plenum fan, but a plenum fan will likely have lower discharge sound levels. Let's look at another example. A discharge plenum is often added downstream of a housed fan to reduce discharge sound levels or to provide more flexibility, like multiple duct connections or to allow for an abrupt change in direction. But as I mentioned, a housed fan is at its best when discharging into a straight section of duct. When a housed fan discharges into a plenum, the energy losses result in increased fan power.
In our example, adding the discharge plenum to the housed fan increases its brake horsepower from 11.8 to 13.2 since it no longer discharges into a straight duct. This is still lower than the belt drive plenum fan, but now the input power for the housed airfoil fan is higher than the direct drive plenum fan. But adding the discharge plenum does allow the housed airfoil fan to achieve similar discharge sound levels that are fairly close to the plenum fans. In this example, the direct drive plenum fan is still the quietest, especially in these low frequency octave bands that are difficult to attenuate.
So, when a discharge plenum is added to a draw-through house fan, it results in more fan power being consumed, typically to the point where a direct drive plenum fan has about the same power consumption as the housed airfoil fan. And discharge sound levels are similar, if not better, with the plenum fan. But the air handling unit with the plenum fan will likely be shorter. In this example, adding the discharge plenum to the housed fan increased the overall length of the air handling unit by more than 3 feet. When multiple supply duct connections are desired, a housed fan requires a discharge plenum to allow for the multiple connections. With a plenum fan, multiple duct connections can be made to the fan section itself, eliminating the need for a discharge plenum and resulting in a shorter unit. Due to installation restrictions, it's often unlikely that a house fan can be installed in the ideal configuration as shown in example 1. This makes the use of discharge plenums and multiple supply duct connections fairly common. Let's look at one more example. In some applications, final filters are included as the last section in the air handling unit.
When a house fan is used, a diffuser section must be added downstream to provide even airflow through these final filters. This is not a requirement for the plenum fan since it pressurizes the surrounding plenum and provides even airflow through the filters with minimal downstream distance. In this configuration, the input power for the housed fan increases due to the pressure drop of the diffuser and the fact that the house fan is no longer discharging directly into a straight section of the duct. For our example, the direct drive plenum fan requires the least amount of power, 14.1 horsepower compared to 15 for the housed airfoil fan.
Let's summarize this discussion of housed versus plenum fans. When discharging into a single, sufficiently long, straight section of duct that is about the same size as the fan outlet, a housed fan will likely require less power than a plenum fan, but a plenum fan will likely have lower discharge sound levels. If a discharge plenum is added downstream of a housed fan to reduce sound levels or to allow for discharge flexibility, a direct drive plenum fan will likely require less power than a housed airfoil fan, with similar or superior discharge sound levels. Additionally, the plenum fan will likely result in a shorter air handling unit. When downstream sections are present, such as a discharge plenum, final filter, gas heater, or even a blow-through cooling coil, a direct drive plenum fan will likely require less power than either a housed or belt-driven plenum fan. Before we lead the discussion of plenum fans, let's discuss the use of direct drive rather than belt drive plenum fans, which have allowed for some changes to traditional paradigms when selecting a fan. Historically, the diameter and width of the fan wheel would often be predetermined by the fan manufacturer of the air handling unit. The variable open to change was the rotational speed of the fan shaft, or RPM, which was adjusted using belts and sheaths. Today, direct drive plenum fans are available in various wheel diameters and wheel widths. Even though there are no belts and sheaths to adjust speed, the fan can be operated at various speeds by a VFD. In a sense, the VFD on a direct drive plenum fan replaces the drive kit that would be used for a belt-driven fan. Most people think of a VFD as being used to reduce the speed of the fan, from the motor synchronous speed to some minimum turn-down limit of the VFD. However, the VFD can also be used to operate the motor above synchronous speed. This provides the opportunity to use one of two selection approaches. The first, which we'll refer to as synchronous speed selections, operates the motor at its synchronous speed, typically 1800 or 1200 RPM. The diameter or width of the fan wheel is then changed to achieve the desired performance. Flexible speed selection is a relatively new concept in the industry. With this approach, the width of the fan wheel is held constant and the diameter or speed of the fan is then changed to achieve the desired performance. As an example, the VFDs and motors that Trane uses for direct drive plenum fans and air handling units can operate up to at least 90 Hertz, which equates to about 2700 RPM for a nominal 1800 RPM motor. Flexible speed selections typically allow for a more efficient and quieter fan choice. Let's look at an example.
Using the same example VAV air handling unit, here are two selections for a 30-inch diameter direct drive plenum fan. The first row shows a synchronous speed selection, and the second row shows a flexible speed selection. For the first selection, the motor's nominal speed is 1800 RPM. To deliver the desired airflow and static pressure, the width of the fan wheel is trimmed down to 57% of nominal width for this particular wheel diameter. And the motor operates at its synchronous speed of 1780 RPM. For the flexible speed selection, however, the fan wheel is kept at its nominal width. To deliver the same desired performance, the fan wheel need only rotate at 1320 RPM. Here we can use a 1200 RPM motor and operate it above synchronous speed by running the VFD at about 66 Hertz rather than at the nominal 60 Hertz. The resulting input power drops from 15.4 horsepower for the synchronous speed selection to only 12.8 for the flexible speed selection. And because the fan operates at a reduced speed with a wider wheel, the flexible speed selection will typically result in lower discharge sound levels.
As with anything, there are drawbacks to using the flexible speed selection process. 900 and 1200 RPM motors are less common than conventional off-the-shelf 1800 RPM motors, so they can be more expensive. Also, these smaller motors are often less efficient, so be sure to include motor efficiency, not just brake horsepower, when comparing fan selections. One final way to characterize centrifugal fans is whether a single fan wheel is used or if a multiple fan array is used. Historically, most air handling units have used a single fan wheel, although the use of a few fans in parallel has been somewhat common. Over the last several years, however, the use of 4 or more fans in an array has increased in popularity. A fan array uses multiple, smaller fan wheels arranged in parallel airflow paths. Typically, direct drive plenum fans are used in the array. The example in this picture shows a 4-fan array. Fan arrays have some advantages over using a single fan wheel, but they also have drawbacks. The primary benefits of using a multiple fan array are a possible reduction in overall length of the air handling unit and redundancy in the event of a failure. The distance or spacing required both upstream and downstream of a fan is typically a function of the fan wheel diameter. Therefore, if multiple small diameter fan wheels are used, the upstream and downstream spacing required will usually be less than if a single large diameter fan wheel is used. In many cases, this can shorten the overall length of the air handling unit. However, there is a bottom threshold to this length reduction. First, there is a certain amount of space needed upstream or downstream to allow the fans to be serviced or replaced, if necessary. This includes space for a person and for a fan motor and/or wheel when the fans are stacked in multiple levels. It may also require space for a ladder and possibly a mechanical hoist. Next, for applications where an inlet or discharge connection is made to the top, bottom, or side of the fan section itself, additional space may be required to properly load or unload all fans in the array. Finally, motorized control or backdraft dampers are sometimes used to prevent backflow through an inactive fan. Isolation dampers on the discharge side may be provided to allow a fan to be serviced or replaced while the other fans remain operational. These components will typically add length to the unit. To demonstrate the potential to reduce unit length, let's look at another example.
This example is for an air handling unit selected to deliver 15,000 CFM. In this case, the fan is located upstream of the cooling coil, making this a blow-through configuration. When a single 33-inch diameter fan wheel is used, the minimum spacing required upstream is about 20 inches. If two smaller fan wheels are used in an array, the upstream spacing is reduced to about 15 inches. As the number of fan wheels continues to increase, this upstream spacing required continues to decrease. But you can see that the incremental benefit is greatest going from 1 to 2 fans, and not as much as the number of fans continues to increase. But as Dustin mentioned, there is a certain amount of space needed to allow the fans to be serviced. The typical recommendation for upstream clearance is 18 inches, but we use the absolute minimum of 12 inches for this example. You can see here that when 4 fans are used, the upstream spacing required is dictated by the need for service access rather than by fan wheel diameter. So there is no further benefit of length reduction by using more fans. Let's look at the downstream side of the fan. With a single fan wheel, the minimum spacing required downstream is about 51 inches. This is the distance from the inlet to the leading edge of the impeller, plus any downstream spacing required for airflow. Similar to upstream, as the number of fan wheels increases, this required downstream spacing decreases. But notice that the length of the fan plus motor, the direct drive motor mounted at the end of the shaft, is longer than the downstream spacing required. So for this example, the downstream spacing for airflow distribution is not the limiting factor. It's the length of the fan plus motor. Of course, as multiple fans are used, the smaller fan wheels and smaller motors are shorter, so the downstream length is lessened. Again, the benefit is greatest going from 1 to 2 fans, but the incremental benefit is less as the number of fans continues to increase. Now, the typical recommendation for downstream service clearance is 24 inches, but we use an absolute minimum of 18 inches for this example. Also, we're assuming the fan section has access doors on both sides. If instead it had a door on only one side, additional access space would be required downstream to allow the opposite side fan to be serviced or replaced for the 2-fan configuration. And once you go to 3 or 4 fans, you certainly need this extra space downstream to access the middle or upper fans. So the total downstream length is dictated by the length of the fan plus motor plus any downstream service clearance required. The length reduction is greatest going from 1 to 2 fans, but due to the need for service access, might actually increase when more than 2 fans are used. Here is the result of adding the upstream and downstream distances. When a single fan wheel is used, the overall length of the fan section is about 74 inches. If 2 smaller fan wheels are used, the overall length is reduced to about 57 inches. Again, assuming doors on both sides. While length can be reduced significantly by changing from 1 to 2 fans, the potential length reduction diminishes as the number of fans continues to increase. And like in this example, due to the need for service access, the length may actually increase when more fans are used.
When more than about 4 or 6 fan wheels are used in an array, the upstream and downstream spacing requirements begin to be dictated by the need for service access rather than by fan wheel diameter, so there is typically little further length reduction benefit. As I mentioned, another benefit of using a fan array is that it can provide some level of redundancy. If one fan fails, the other fans are still able to provide some or all of the airflow. Of course, this assumes that the fans were selected to provide this redundancy up front.
Using the same 15,000 CFM air handling unit, this table shows the redundancy that can be achieved by using two fans in array. The first row shows the selection at design conditions. With both fans operating, each fan delivers 7,500 CFM and requires a 7.5 horsepower motor. Now, in order to provide 100% redundancy, if one fan was to fail, the other fan must be able to deliver the design airflow by itself. So as shown in the second row, for either one of these fans to deliver 15,000 CFM, it must be equipped with a 20 horsepower motor, not the 7.5 horsepower motor. So for this example, a two-fan array can provide 100% redundancy as long as each fan is equipped with a larger motor. The downsides of the increased motor size are reduced motor efficiency and increased electrical requirements. Now, as a side note, what happens if the motor sizes are not increased? In this two-fan array, if one fan fails, the remaining fan is capable of delivering up to 70% of design airflow. So if 70% is an acceptable level of redundancy, you wouldn't need to upsize the motors. Let's look at a 3 or a 4-fan array. For the 3-fan array, at design conditions with all three fans operating, each fan is selected to deliver 5,000 CFM and requires a 7.5 horsepower motor. As shown in the second row, if any one of the fans was to fail, the remaining two fans could still deliver the full 15,000 CFM. Each fan is able to deliver 7,500 CFM using the same 7.5 horsepower motor. The same is true for the 4-fan array. If any one of the fans was to fail, the remaining three fans could deliver the designed supply airflow without needing to upsize the motors. So for this example, if 100% redundancy is required, any of these configurations can work. The 2-fan array requires the lowest total input power when all fans are operating, 13.1 compared to over 14 for the 3 or 4-fan arrays. But it does require equipping each fan with a larger motor. Either the 3 or the 4-fan arrays can provide 100% redundancy without changing the motor size. The 4-fan array requires the lowest total input power when one fan is failed, but it requires the most power when all fans are operating. So assuming that a fan will be fixed or replaced when it fails, it seems like you would put more emphasis on how the array performs when all fans are operating, rather than one fan has failed.
While fan arrays have some advantages, there are also drawbacks compared to using a single fan wheel. When a multiple fan array is used, there are advantages of using fewer, larger fans, like 2, 4, or 6 fans, versus many smaller fans, like 9, 12, 24, or even more. Trane has published an engineering bulletin that goes into more detail on all of these advantages and drawbacks. It's listed in your bibliography, and the literature number is on this slide. To summarize, as we demonstrated, a fan array will typically reduce the overall length of the air handling unit. The length reduction by going from 1 to 2 fans is great, but the incremental length reduction benefit is not as significant as you continue to increase the number of fans. Eventually, you hit a minimum threshold dictated by service clearance. When multiple fans are used, the air handling unit can provide some level of redundancy. Of course, this requires proper selection to ensure that when one fan fails, the remaining fans are able to provide the required airflow. In most cases, an array of 3 or 4 fans is able to provide the same level of redundancy as an array with many smaller fans. Another benefit of using a fan array is easier serviceability. When multiple smaller fans are used in the same array, the fans or motors are lighter and easier to replace if necessary. Using a single fan wheel will typically result in the lowest cost air handling unit. When a fan array is desired, using fewer, larger fans will typically cost less than using many smaller fans. Using a single fan will typically require less power than an array with multiple fans. When a fan array is desired, using fewer, larger fans will typically require less power than using many smaller fans. In many cases, the fewer the number of the fans, the better the acoustics. Fewer moving parts and therefore fewer fans generally results in better reliability. Of course, the redundancy provided by using multiple fans partially offsets the concern over a fan failing. Bottom line, fan arrays can reduce the overall length of the air handling unit, provide redundancy for critical applications, and allow the fans and motors to be more easily replaced. But they are typically increase the cost of the air handling unit, require more input power, and have higher sound levels. When a multiple fan array is desired, using fewer larger fans, like 2, 4, or 6, will typically be a better overall solution than using many smaller fans. As shown earlier, 2 fans can reduce unit length, 3 fans can provide 100% redundancy without a significant increase in motor size, and 4 fans can accomplish the same while fitting within a normal aspect ratio. No more than 6 fans are needed to completely eliminate 900 RPM motors in units up to 60,000 CFM. One final comment. The examples that John and I went through during this broadcast are also included in a recently published Engineers Newsletter. If you didn't get one yet from your site coordinator, you can download it from Trane.com.
Now let's talk about fans applied in HVAC systems. Here's a simple constant volume system. Selecting a fan for it seems pretty straightforward. First, determine the air handler size based on the supply airflow needed to control zone temperature at design conditions. If this system needs 9,000 CFM, a size 14 air handler would work. Next, find the total static pressure drop for the system from the fan outlet all the way around to the fan inlet. This pressure drop depends on operating conditions. It's low when the coil is dry and the filter is clean, but it's high with a wet coil and dirty filter. Third, choose a fan to analyze. In this case, a 16.5-inch FC fan might work. Now, we can simply plot the design airflow and total static pressure on the fan curve to find the required fan speed, right? Yes, provided we also comply with some fan selection rules. First, don't exceed the maximum airflow. Even though the fan could produce it, too much airflow and velocity can be noisy or damage equipment. Second, don't exceed maximum brake horsepower for the fan. If you do, the motor will probably trip out on overload. Third, don't exceed the maximum static pressure. Excessive negative pressure upstream or positive pressure downstream might cause air or water leaks and might even damage the unit casing. Fourth, don't exceed maximum fan speed. Rotating machines have mechanical limitations. Fifth, don't pick a fan that will operate in the do not select area to the left of the surge line. A fan in surge can cause airflow and acoustical problems. Finally, do not select a fan that uses less than the minimum brake horsepower. A small motor on a big fan might not have enough torque to get the fan moving. Be sure to follow these rules and only select a fan that stays within the selection envelope at all operating conditions. Don't let a good selection at design conditions become a bad selection during normal operation. Incidentally, if you use data tables or a selection program, these rules are already built in. Okay, let's select the fan and fan speed. Start by plotting two system resistance curves based on the highest and lowest expected pressure drop at 9,000 CFM. If we assume the duct connections to this air handler are very good, with no tight turns or transitions at the inlet or outlet, there's no need to account for a system effect. But John will cover that aspect of fan selection a little later. Anyway, if we use the high pressure system curve, we find that the fan would deliver design airflow at about 1350 RPM, but this point is outside of the selection envelope. It takes too much horsepower. And at the dry coil clean filter condition, this constant speed fan would try to deliver over 10,000 CFM and require even more horsepower. Obviously, this fan selection won't work. A bigger fan or a different fan type would be needed. On the other hand, if we use the low pressure curve, we find that the fan would deliver 9,000 CFM at about 1,200 RPM. At the wet coil, dirty filter condition, system resistance rises, so the constant speed fan delivers only about 8,000 CFM at a higher pressure, but using less horsepower. These two operating points are within the selection envelope, so this fan would work, but it doesn't deliver 9,000 CFM at all conditions. So what's the lesson? For constant fan speed systems, which most people call constant volume systems, designers must consider both the highest and lowest expected system resistance, then decide what's more important. If you select a fan that works at the highest resistance, it delivers more than enough air at all loads, but higher airflow usually means less dehumidification and it takes more horsepower. On the other hand, if you select a fan that works at the lowest system resistance, it delivers less than design airflow at some conditions, and less airflow usually means better dehumidification and it takes less horsepower. If it was up to me, I'd probably select a fan for the low system resistance, but whichever approach you choose, remember that a constant speed fan delivers more air and uses more horsepower when the filters and the coils are clean, not when they're dirty. And one more thing, do not select a fan too close to the surge line. For example, if you select at point A, the fan could cross into the do not select area at point B. Let's switch to a VAV example. Here's a VAV system with a VFD-controlled supply fan and a relief fan. Again, our example needs 9,000 CFM of supply air at design, so a size 14 air handler would work. But selecting this supply fan might be a little more complicated than it was for the constant volume system because airflow varies. Each VAV zone defines a different airflow path. The highest total static pressure drop in each path is the sum of all pressure drops in that path. The table shows the lowest and highest pressure drop at design airflow in the path through Zone 1. By inspection, we see that Zone 1 path has the highest pressure drop because it's furthest from the fan. The total static pressure drop is only 4.7 inches with a clean filter and dry coil, but it's 5.8 inches when the filter is dirty and the coil is wet. Of course, the highest pressure drop path could be through any zone, so if it's not obvious, we should really calculate pressure drop for each path at design conditions and use the highest value. Since the pressure for this system is pretty high, we'll try an 18-inch airfoil fan. As with any fan, this one has a selection envelope. The fan must operate within this envelope at all conditions. To assure design airflow, we use the high pressure system curve and find that this fan delivers 9,000 CFM at about 2,600 RPM. With a clean filter and dry coil, it delivers design airflow at 2,400 RPM. This fan stays within the selection envelope at both design conditions, so it works so far. At part load operation, zone loads drop, so the VAV boxes close. Supply airflow drops, and the system curve rises to some new level. Duct pressure increases, so the fan slows down. If airflow drops to 5,000 CFM, we need to verify that the new fan speed is still within the selection envelope. The fan speed depends on sensor location, pressure set point, and the current system curve. With the sensor located near Zone 1 and set to maintain the duct at 1.3 inches above outdoor pressure, the fan operates somewhere within the shaded area shown. Although we could calculate the predicted operating point more accurately, like we showed in your handout, we usually keep things simple by assuming that the fan operates at the intersection of the system curve and the design VAV modulation curve defined by this equation. In this example, we conclude that the fan operates at about 1,600 RPM, delivering 5,000 CFM at about 2.7 inches. So this fan selection works fine, as long as the airflow is more than about 30% of design. The fan doesn't cross the surge line. You should always check system operation at the lowest expected part load airflow. If the system operates in the do not select area, you should consider a different fan or control approach. Designers, or perhaps installers, often locate the duct pressure sensor in the equipment room near the fan outlet and set it at a high control pressure, say 2.9 inches. The modulation envelope changes. Assuming again that the fan operates at the intersection of the part load curve and the design VAV modulation curve, we see that the boxes must close more and that the fan delivers 5,000 CFM at about 3.8 inches. This fan selection still works at this airflow, but it takes more horsepower. And the fan can't operate much below about 50% of design airflow without crossing the surge line. So move the sensor away from the fan to reduce duct pressure, save fan horsepower, and increase operating range. Fan energy can be reduced even more by resetting the duct static pressure set point to keep one box nearly wide open. This lowers the system curve and the fan modulation envelope shrinks considerably. Sensor location isn't as important because its set point changes with load conditions. This approach reduces fan horsepower and prevents surge even at low airflows. We've discussed this kind of fan pressure optimization many times in the past, so we don't cover it in detail here. Just remember, it saves energy and Standard 90.1 requires it on many VAV systems. VAV systems operate in several modes. Fans selected for cooling usually work fine for economizer operation. During morning warm-up, however, supply airflow must be high enough for the heat exchanger, and the actual fan operating point depends upon system control. One common control approach forces all VAV boxes wide open. This causes the system curve to drop, as shown, for example. With duct pressure control disabled, the fan operates at its maximum speed. If maximum speed equals design speed, the fan tries to deliver almost 11,000 CFM at 2,600 RPM. This exceeds the airflow limit. Either a larger fan or more likely a larger air handler would be needed for this much airflow. So if you set a max speed, be sure it's not set too high. Some fans include piezo-based inlet flow measuring devices that do not cause turbulence or acoustic problems. With these sensors, another control approach can be considered. Again, with the boxes wide open, the duct pressure control disabled, the supply fan speed can be modulated to maintain fan airflow at 9,000 CFM. The selected fan can certainly handle this, and the heat exchanger gets plenty of airflow. A third approach forces the VAV boxes to a specific airflow, say 80% of design, rather than wide open. Duct pressure can be controlled and the fan speed would decrease to deliver an acceptable lower airflow. The bottom line, whatever approach you use to control the fan during morning warm-up, be sure that your fan selection can accommodate it. Some VAV systems use return ducts, so they need a return fan rather than a relief fan. The supply fan takes care of all supply side pressure drops, while the return fan takes care of the return side. Supply fan selection is similar to our previous discussion, but with lower total static pressure. Return fan selection, however, can be tricky, primarily due to morning warm-up operation. Since the outdoor air damper is closed, the supply and return fans are in series. Both fans handle the same airflow, which must be high enough for the heat exchanger, but not too high for the fans selected. In quick summary, if the return fan is selected for a design airflow of 7,500 CFM, then the supply fan flow probably needs to be controlled during morning warm-up to limit its airflow to 7,500 too. On the other hand, if the heat exchanger really needs 9,000 CFM, the return fan must be selected to deliver it. And however the return fan is selected, controls must be carefully designed to assure proper operation of both fans in all modes. This can be a big challenge, but we don't have time to cover it today. I hope that a future Engineers Newsletter can address these return fan selection and control issues in more detail. Who's next?
Turbulence caused by airflow restriction at either the fan inlet or outlet, or non-uniform air distribution, can negatively impact the performance of the fan when it's installed in an air handling unit or connected to a duct system. This is commonly called system effect. System effect prevents the fan from operating as it did under laboratory rating conditions. System effects related to the fan inlet or outlet generally occur when the air is not allowed to establish a uniform velocity profile as depicted here. If an elbow, a branch, turning vanes, or a damper is located too close to the fan outlet, this system effect should be accounted for during fan selection. Likewise, if an elbow, turning vanes, air straightener, or other obstruction is located too close to the fan inlet, this system effect should also be accounted for. Additionally, the effects of pre-swirling the air prior to entering the fan wheel or the use of an inlet plenum or cabinet must also be considered. Now, as Dennis mentioned, manufacturers of air handling units or package rooftops typically account for many of these effects when they occur within the manufactured assembly. For example, in a draw-through arrangement, the effects of the surrounding cabinet or the discharge from the unit are typically included when determining and cataloging fan performance. The bigger challenge for a design engineer are the discharge duct connections or any components that are added in the field. As I mentioned, a system effect prevents the fan from operating as it did under laboratory rating conditions. But generating a new fan performance curve for every possible system effect would be too cumbersome and confusing. So for simplicity, AMCA has published several system effect correction factors to help design engineers account for many of these effects before the fan is selected and installed. Let's look at an example using AMCA's publication 201 titled Fans and Systems. Now, locating an elbow too close to the fan discharge is a very common cause of system effect. This figure depicts 4 possible arrangements for this elbow. Let's look at an example where the elbow is in position A and is connected directly to the fan discharge. The severity of the system effect depends on air velocity and the distance from the fan outlet, which is given in terms of effective duct length. The AMCA publication explains how to calculate 100% effective duct length, but for our simple example, we're assuming no outlet duct between the fan and elbow. Assuming a certain fan outlet ratio and no outlet duct, when the elbow is in position A, this table tells us to refer to curve R or S. Now, these curves are included in figure 7-1 of the AMCA publication. If the discharge velocity is 2,500 feet per minute, we go up to intersect curve R or S, and we find that the system effect factor for this example is estimated between about 0.3 and 0.45 inches of water. So when selecting a fan, this system effect factor is like an effective pressure drop that should be added to the estimated static pressure drop for the rest of the system. For example, say we are selecting a fan to deliver 9,000 CFM, and we have estimated the total static pressure drop to be about 1.8 inches. This fan would need to operate about 800 RPM and 5.3 brake horsepower. Now, to account for the system effect due to the elbow too close to the fan outlet, we should add between about 0.3 and 0.45 inches to our estimate when selecting this fan. Using the high end of this range, if we add 0.45 inches to our estimate of 1.8 inches, we should select the fan for 2.25 inches of static pressure. Because of this system effect, this fan will need to operate at a higher RPM, about 875 RPM versus 800, and will require about 15% more power, 6.1 horsepower versus 5.3. In this case, it will also generate higher sound levels. If we don't account for this system effect during fan selection, a constant speed fan will not deliver the desired airflow. If it's a VAV system, the fan will speed up to deliver the necessary airflow, but will consume more power. So to have your fan perform as desired, pay close attention to how you connect ducts to the air handling unit.
The acoustical impact of fan choices has been mentioned already during this broadcast, but let's take a closer look at how to select a quiet fan. I'll start with a simple example, the propeller fan, used primarily outdoors on condensing units and air-cooled chillers. Significant development time goes into designing low-noise propeller fans, but when outdoor fan sound is a problem, you typically only have three choices. You can either move the unit further away, choose a low-noise fan option if it's available, or use path attenuation as needed to reduce the sound to an acceptable level. Many times the choices for quieting indoor fans are also limited. This is the case for packaged equipment that comes with one fan type and no sound attenuating options. However, some indoor units have several choices of fan type, size, or other options that may impact the sound leaving the unit. Let's look at how to select a unit for good acoustics. The sound created by a fan is based on the type of fan, flow rate through the fan, total pressure, and the fan efficiency. That's just for the fan alone. When a fan is placed in a unit, drive system components and flow disturbances at the inlet and outlet change the sound produced by the fan. Once the sound leaves the fan, it is further impacted by other components of the unit. If the fan discharges directly into a duct system, the duct can also change the sound produced by the fan. There are two developments that have greatly improved your ability to choose a fan with the best acoustics for your application. The first is ASHRAE 260 Sound Test Standard for ducted air moving equipment. This standard accurately accounts for how sound for a given fan changes with flow, pressure, and size. It also accounts for all unit-based sound changes, including flow disturbances and cabinet effects. That means you know exactly how much sound is leaving the unit. Prior to the introduction of Standard 260, a common practice was to test the fan in a standalone configuration and then apply calculated unit effects. Depending upon the fan and the unit interaction, this method could be off by more than 10 dB, even for simple unit configurations. When you compare sound data from different manufacturers, be sure that they all have sound data taken in accordance with Standard 260 so that you are comparing apples to apples. Refer to our Engineers Newsletter on sound ratings for additional information. The second development is easy-to-use selection programs. These programs allow you to see the acoustical performance of various unit choices. John gave an example of this when he compared the performance of an airfoil fan in housed and plenum configurations. In his example, adding a lined plenum section to the housed airfoil fan resulted in considerable reduction in sound leaving the unit. These two developments eliminate the need to rely on rules of thumb to choose one fan type over another. While a rule of thumb can provide general guidance, it can also have exceptions and might only apply to some applications. To illustrate, we used a selection tool to run 9 different fan choices for a single design condition. The table summarizes the octoband sound power data and numerically ranks the prospective selections based on individual comparisons of tip speed, outlet velocity, brake horsepower, and static efficiency. None of the fans excelled in all categories. So which fan is the best fit for the application? Well, remember that the selection program provides unit sound. The acoustical impact of the system must be considered to determine which fan will be the quietest in the occupied space. As a result, octoband data provides the most accurate indication of equipment-generated sound and should be used to identify the quietest selection. The best general guidance to follow when using a selection program to find a quiet fan is to explore all fan and unit options. If you reject a fan based on a rule of thumb, you might miss the best fan for your application. And remember that unit choices also have an impact on sound. Options like lining the unit or adding a plenum section can dramatically reduce the sound leaving the unit. One final point about selecting quiet fans is to note where the operating point lies on the fan curve. Earlier, Dennis talked about the do not select or stall line on the fan curve. Avoid selections near this line. Fans enter a region of acoustical stall prior to entering aerodynamic stall. When operating an acoustical stall, the fan will reliably move air. However, the sound produced by the fan will be erratic. Each fan design is different in terms of how acoustical stall process develops. Some fans make a rapid transition into stall. This rapid transition is common with airfoil fans, regardless of whether they are housed or unhoused. Other fans have a gradual transition into stall, making it difficult to determine where the acoustical stall line lies on the fan curve. This is more common, but not universal, with forward curve fans. The only reliable method to determine the conditions at which acoustical stall occurs is to review the change in sound during the rating test. As fan flow is reduced along a constant speed curve, the fan usually gets quieter. However, once the operating point enters acoustical stall region, the sound begins to increase. When a fan transitions abruptly into acoustical stall, the change in sound can be sudden and highly variable, which makes it difficult or impossible to provide accurate sound data. Sound level increases of 5 to 10 dB are typical, but it may be as high as 20 dB. The increases can be in any octave band, but most often show up in the difficult to attenuate low frequency range. As a result, the increased sound is more likely to result in noise. Also consider that unit operation is not constrained to the design point. The design selection point might not match the actual operation point, or the VAV fan unloading curve may cross into the acoustical stall region as shown on the slide. In summary, remember the following 3 points when selecting and comparing quiet fans. Sound data taken in accordance with ASHRAE Standard 260 provides the best indication of sound produced by the entire unit. Selection programs allow you to compare all fan and unit options. And finally, avoid rules of thumb. Octave-band sound data is needed to determine which fan is the quietest. Dennis, are there any common fan problems that you hear about?
Well, sure, but hopefully with all the fan selection information we've covered so far, most fan system problems can be avoided. Once installed and commissioned, air handlers usually meet or exceed expectations, but sometimes they don't. The most common fan problems that we hear about are less than expected airflow and more than expected noise. Dave will discuss noise-related problems in a minute, so I'll talk about insufficient airflow. It usually results from either a poor estimate of duct system resistance or failure to account for system effect at the air handler connections. It's hard to predict from a drawing how a duct system will actually work after it's installed, but duct sizing programs can do a pretty good job at this. If you rely on rules of thumb to estimate system total static pressure, you may find yourself increasing motor horsepower on many jobs. And architects always seem to want small equipment rooms. Tight spaces lead to less than ideal duct connections at the air handler. The resulting system effect must be accounted for during design or dealt with after installation. And speaking of installation, don't forget to visit the construction site and monitor duct installation. Even innocent modifications can unexpectedly change either system resistance, system effect, or both. For more help solving airflow shortfalls, you should turn to the AMCA publications. They can help you discover problems and devise solutions. AMCA 201 lists several possible causes for insufficient airflow, all of which seem to relate to either duct design, system installation, field measurement problems, or system effect. It also includes extensive guidance for proper system effect accounting. AMCA 202 includes checklists and recommendations to help you troubleshoot and correct problems found in fan installations. It adds to the list of possible causes. For instance, a fan may have been damaged prior to installation, or it may not be properly wired or controlled. Some designers want to verify fan performance in the field to make sure the fan works as predicted by the manufacturer's fan curve. I always think Does your duct system look like this test chamber? Because if it doesn't, the as-installed fan curves won't be the same as the catalog fan curves. And it's not easy to duplicate published fan curves in the field. AMCA 203 includes detailed guidance for designing and performing field tests. Taking measurements in the field can be difficult, and you don't always have access to the right measurement location. So it's key to understand how to make necessary corrections. But field performance tests are never easy and not nearly as accurate as lab tests. So although verifying fan performance in the field is not impossible, it's probably not your first course of action for correcting airflow shortfalls. And now for some thoughts about noise. Dave?
The most common complaint I hear about is fan noise. All types of air-moving equipment have the potential to be noisy. Fans generate sound, and if that isn't taken into consideration, the result can be noise. I think most noisy fan complaints can be divided into 3 categories. I'll call them unit defects, selection misses, and duct flow problems. Checking for a unit problem is a good first step. These problems can typically be resolved quickly. I rarely see problems with a defective fan, but I have seen cases where something simple, like an overlooked shipping restraint, was causing a problem. Failure to consider acoustics during selection is the most common cause for sound problems. The information I provided earlier gave selection tips for picking a quiet unit. But what I didn't talk about was just how quiet the unit needs to be. That depends on the required space sound levels. Selecting the right fan should include a review of the required sound levels in the occupied spaces and a determination of how the sound will change between the unit and the occupied area. We call this process source path receiver acoustical analysis and have covered it in other broadcasts. If you want a refresher, please review the applications manual on fundamentals of acoustics. When the acoustical goals for the occupied space are known, use an acoustical analysis tool, like the Trane Acoustics program, to create a path analysis. Once the path analysis is made, it's easy to see how unit and system changes will affect the sound in the occupied areas of the building, so that you can then select the right unit for the application. But the majority of sound complaints come from jobs without acoustical goals, where sound isn't even considered when the unit and system choices are made. Doing a quick acoustical analysis, even when there aren't stated sound goals, will help you prevent these noise complaints. The final category of noisy fan complaints is the most challenging. These are the sound problems caused by the design of the ductwork. It is often assumed that all sound in the air system originates at the fan. What is overlooked is that any duct element that generates turbulence will also generate sound. ASHRAE has equations that can be used to calculate the sound generated by common duct elements, like elbows and junctions. The equations were developed by testing duct components in a sound lab. Each component was tested in a variety of duct sizes over a range of airflows. As a result, we can predict the acoustical impact of these common components. Unfortunately, the equations don't apply to the many creative configurations that are developed on the job site. It is unknown how changes in duct size that occur during a turn, abrupt transitions, or closely coupled duct components perform acoustically. Experience has shown that a convoluted air path can create considerable low-frequency sound. In many cases, the sound energy is below 63 Hz and may even be below the audible range. This low-frequency sound is difficult to attenuate and may have sufficient energy to move lightweight building components and gypsum board walls. The resulting noise and vibration is difficult to correct. Attenuation is costly and in most cases ineffective. Often the only remedy is to remove the problem areas of ductwork by relocating the unit and rerouting the ducts. As I mentioned, we don't have modeling tools that show the acoustical impact of these unique duct designs, but there are some general guidelines that will help prevent installation-related problems. First, assume that the air leaving the air handler has an uneven velocity profile and needs at least 3 times the largest discharge opening dimension of straight duct to stabilize. This is especially true for duct discharge units where the fan discharges directly into the ductwork. The system effect issues that John mentioned can dramatically degrade the acoustical performance. For these units, both the distance from the fan and the direction of the first turn are important. The ASHRAE Handbook and the ASHRAE Practical Guide to Noise and Vibration Control provide guidance on selecting discharge configurations to minimize sound problems. Consider using unit configurations or options that will align the discharge opening of the unit with the duct path. Examples include a stacked air handler that allows the fan to discharge into a straight run of duct, or a plenum under a rooftop unit to line the supply and return openings with the duct shaft. Use factory supplied plenums with tested acoustical and pressure drop data. I know of several cases where a field erected plenum was used with good intent, but the design of the plenum caused more problems than it solved. There is more to effective plenum design than mounting a big box on the discharge of the unit. Second, close coupled fittings that result in changes in airflow direction should be avoided. When an airstream is forced to change directions, the velocity profile across the duct also changes, causing turbulence in the air leaving the component. If the velocity profile is not equalized before the next change in direction, the turbulence can create unexpectedly high pressure drop and noise. Sometimes reducing the overall velocity by increasing the duct size can reduce the turbulence and quiet the airflow. Another common feature of problem jobs is large aspect ratio ducts. These ducts are well suited to transferring low frequency sound into the building. If possible, replace the single large duct with multiple smaller ducts from the unit. And finally, locating air moving units away from sound sensitive areas is always a good idea, but it is even more important when duct compromises are likely to be an issue. You probably recognize these guidelines as standard good duct design principles. The fact that they are followed most of the time is part of the reason why noise isn't a problem on every job. Good duct design, coupled with proper unit selection, will prevent fan sound from becoming unwanted noise. The final section of today's broadcast is on the Standard 90.1 fan energy requirements. John, what does the standard say about fan efficiency?
Because the energy use of a fan depends heavily on the design of the air distribution system, simply requiring a minimum efficiency for the fan is not sufficient. Therefore, ASHRAE Standard 90.1 prescribes a maximum allowable limit for the overall fan system power. This limit applies to the sum of all fans that operate at peak design conditions, which is typically peak cooling load. The 2007 version of ASHRAE 90.1 includes two options for compliance. Option 1 is based on nameplate horsepower, while Option 2 is based on brake horsepower. Option 1 is easier to apply and easier for a code official to verify, but Option 2 is more flexible. To comply using Option 1, the sum of the nameplate motor horsepowers for all fans that operate at peak design conditions must be no greater than the value listed in the table. For example, if the design supply airflow for a VAV system is 30,000 CFM, the total allowable nameplate motor horsepower is 45. For a VAV system, this would include the supply fan and possibly either a return fan or a relief fan if it operates at design cooling conditions. And if series fan power VAV terminals are being used, they would also be included since they operate at design cooling conditions. Now note that individual exhaust fans are exempt and don't have to be included in this calculation if their motor nameplates are 1 horsepower or less. This is true whether you choose to comply using Option 1 or Option 2. Now Option 2 is based on input power of the fan shaft or brake horsepower. To comply using Option 2, the sum of the brake horsepowers must be no greater than the value listed in the table. For the same example VAV system, using Option 2, the total allowable fan system brake horsepower is 39. Now this is less than the 45 horsepower allowed by Option 1 because option 2 is based on actual input power of the shaft, not nominal nameplate horsepower. This difference allows for any belt or drive losses, motor inefficiency, and safety factor in motor selection. But option 2 also includes an adjustment factor to account for special filters and other devices. An accompanying table includes pressure drop adjustments for things like fully ducted return or exhaust systems, return or exhaust control devices, higher efficiency filtration or air cleaners, heat recovery or evaporative cooling devices, and sound attenuation. Then this pressure drop adjustment is multiplied by the design airflow through the specific device. As an example, consider this 30,000 CFM VAV system that includes a MERV 13 filter and a total energy wheel. We can use the pressure drop adjustment of 0.9 inches for the MERV 13 filter, and for the total energy wheel, the adjustment is based on the pressure drop through the device at design airflow. The filter is installed in the mixed airstream, so the design supply airflow through it is a 30,000 CFM supply airflow. Multiplied by the 0.9 adjustment factor, the resulting horsepower adjustment is 6.5. At design conditions, the outdoor airflow through the supply side of the wheel is 10,000 CFM, with a pressure drop of 0.8 inches. Therefore, the horsepower adjustment is about 1.9 horsepower. Airflow through the exhaust side of the device is 8,000 CFM, with a pressure drop of 0.7 inches. So the adjustment for this side is 1.4. Summing these up, the total adjustment is 9.8 brake horsepower. This takes the total allowable fan system brake horsepower for this example to 48.8, rather than 39 if no adjustments were used. And like with option 1, this limit applies to the sum of all fans that operate at peak design airflow conditions. In our example, this would include the supply fan and the central relief fan, since it operates to draw air through the wheel at design conditions. Note that this is higher than the 45 nameplate horsepower limit allowed by option 1. So for those applications which have one or more of the items listed in the adjustments table, option 2 provides the flexibility to adjust for those devices. For a given project, if the overall fan system power exceeds the maximum limit allowed by ASHRAE 90.1, here are some ways to reduce fan power. First, if you have your choice, don't move as much air. Of course, this should always begin with reducing the load. Improvements to the building envelope, fewer and better windows, and more efficient lighting are all examples of ways to reduce the building cooling load, which would then require less airflow. Also, design the system for a lower supplier temperature, maybe between 45 and 52 degrees, for example, also reduces the airflow required to offset the sensible cooling loads in the zone. Reducing supply airflow allows the system to be designed with a smaller supply fan and a smaller return or relief fan if equipped. One important point though, remember that the fan power limitation prescribed by ASHRAE 90.1 is in terms of horsepower per CFM of airflow. So while reducing supply airflow will certainly save fan energy, whether or not it helps you meet the 90.1 prescribed limit depends. If you downsize the air handling unit and ductwork so much that the airside pressure loss is the same as when you started, it will still result in less fan horsepower, but the horsepower per unit CFM might not change. So if you need help to meet the 90.1 requirements, consider keeping the air handlers and ducts a little larger, not downsizing them so much, to reduce airside pressure loss. This would then result in lower horsepower per CFM. The second strategy is to reduce airside pressure losses. This might include using efficient, low-loss duct fittings or slightly larger ducts, maybe even selecting a larger air handling unit. A smaller unit might have a lower first cost, but it uses more fan power, while a larger unit costs more initially, but uses less fan power. Then also look into low pressure drop filter and coil options. Finally, the third strategy is to select a fan that has a higher efficiency for the specific application. But remember, as we demonstrated earlier, the right fan depends on the application. Forward curved or airfoil, housed or plenum, Belt drive or direct drive, single fan or fan array, they all have their advantages and drawbacks. Now I put these three approaches in this order for a reason. To explain, here's an example FC fan selected to deliver 13,000 CFM at 4.8 inches of total static pressure. At these conditions, the fan would require 15.2 brake horsepower. Now consider if we select a more efficient airfoil fan to deliver the same airflow and pressure. The design of the system has not changed, just a different fan has been selected. Using the more efficient airfoil fan reduces the brake horsepower to 13.9 compared to 15.2 for the FC fan. Now, instead of selecting a different fan, what if we keep the same FC fan but design the system to reduce airside pressure losses by 20%? Maybe by using low loss duct fittings or selecting a slightly larger air handling unit, for example. In this case, the same FC fan would require only 13 horsepower. And finally, what if we kept the same FC fan, the same size air handling unit, and made no changes to the duct system? Instead, we designed the system to supply 50-degree air rather than the conventional 55-degree air. This change would reduce the supply airflow from 13,000 to just over 10,000 CFM. Keeping the same size unit and ductwork, the brake horsepower is reduced to 7.3. So if you have a choice, the biggest reduction comes from reducing supply airflow. The next biggest comes from reducing airside pressure losses, then comes selecting a more efficient fan. Don't just focus on fan type or you'll miss these bigger opportunities. Of course, you could choose to do all three and achieve even more fan power reduction. To summarize this discussion of ASHRAE 90.1, the prescriptive fan power limits apply to the sum of all fans that operate at peak design conditions, which is typically peak cooling load. The 2007 version of the standard includes two options for compliance. Option 1 is based on nameplate motor power, and it's simpler. Option 2 is based on brake horsepower, and it's more flexible for those applications which have one or more of the items listed in the adjustments table. Finally, if you need to decrease fan power, look for ways to reduce airflow by reducing the cooling load or designing for a colder supplier temperature, reduce airside pressure losses, and or select a higher efficiency fan. Incidentally, AMCA has been working on a new standard, 205, which helps to more clearly classify fan efficiency. So you may start to hear the term fan efficiency grade, and it's possible that it might make its way into minimum efficiency standards like 90.1 sometime in the future.
Well, that brings us to the end of today's presentation. Today you've learned that fans used in air handling systems can have a significant impact on energy use and acoustics. Hopefully we've helped you increase your understanding of how to select and apply fans to deliver quiet, efficient air handling systems. As Dustin and John demonstrated, the right fan depends on the application and is often based on balancing efficiency, acoustics, and cost. And Dennis showed us how fans interact with the system, be it constant volume or VAV, and how that impacts selection and control. Dave explained the importance of quality sound data and the impact of the air handling unit on fan sound. Finally, most problems associated with low airflow or noisy operation can usually be avoided through proper fan selection, better duct design, and fan installation, or a little more thought about how the fan will operate as part of the system. Now, there are a number of publications available that provide more information on the material covered today, including several engineers' newsletters, application manuals, numerous articles, and a recently released engineers' newsletter. A bibliography detailing these resources is available from your local site coordinator. Additionally, past broadcasts are also available to order on Trane.com. Please check out the website for information on specific broadcasts. Many of these are accredited for AIA and LEED continuing education. Please remember to fill out a survey and let us know how we're doing. AIA members, remember to turn in your member information to your local site coordinator. Now, we have 2 more engineers newsletters this year. In May, we'll discuss the benefits, challenges, design, and control of central geothermal systems. And in fall, we'll provide an update on ASHRAE 90.1 2010 as it pertains to mechanical systems, controls, and simulation modeling. So mark your calendars. Thanks for joining us today. We look forward to seeing you in May.